to look at the solutions to the homework over confidence intervals for today. We're going to use exactly the same data to do our very last topic in probability and statistics. So I'm sorry I can't be here to do it with you today, but I will make sure that tomorrow we go over our review carefully before we take our final unit test. So we are taking our final unit test tomorrow, so these examples are important. And once we do these examples, you're going to practice all the same things together on the review. I will make sure that eventually today, my kids are sick at home, and eventually today I will get the key to the review on Canvas so you can check it, and we'll look at it carefully before we take our test tomorrow. But it's so important to do this because it brings everything together. So this is called a significance test. So let's reconsider our data about the proportion of WHS students that have an accident while driving. So we already calculated this for the confidence interval. 12 out of 57 is 0.21. So 21% of students surveyed randomly had an accident while driving. So notice this value is lower than the 40% suggested by safetyinsurance.com. But is this low enough to suggest that 40% is unlikely to be the truth for WHS students? Maybe 40% is the truth for WHS students, and we just got an unlikely sample result just by chance. So either that's the case, or maybe 40% really isn't the truth at Westfield. Maybe, in fact, our students tend to be better drivers on average. So if we assume that WHS students are like all other first and second year drivers, then, and now notice what we're doing, we're assuming the truth for our school. We're assuming the truth, the proportion of students that have had an accident is 0.4. And notice this is not a p-hat, that's the real p. We're assuming that the truth for our population at Westfield is just like everybody else, all other first and second year drivers, is really 40%. This is called the null hypothesis. N-U-L-L, and it's written using this symbol, H sub 0. So look, if Westfield students are like everybody else, then the proportion that have an accident while driving is 0.4. Now, if we assume that's true, we're looking for evidence of an alternative, that the truth for WHS students is less than 0.4. Our sample result suggests that, but is this sample result low enough that we can reject this at the truth, and maybe we can think the truth for Westfield High School students is lower? This is our alternative hypothesis. And it's written using the symbol H sub A, so A for alternative hypothesis. So we're trying to decide, can we find evidence that the proportion that have an accident at Westfield High School really is less than the 40%? So the conditions that you have to check are exactly the same as for confidence intervals, except the null hypothesis value up here is used for the true proportion. We're assuming it's true and looking for evidence against it. We do this because the calculations are going to assume the null hypothesis is true. And then we're going to try to decide if our p-hat is unlikely or not unlikely. So guys, you know this, the sample must be random. So the observations in the sample must be approximately independent of one another. Now, this is true by the 10% rule. Look, if you take 10 times the sample size of 57, that's 570. That's clearly less than 2,500 WHS students. So the sample size also has to be large enough to guarantee an approximately normal shape. Well, this is where we look at the number of successes and we look at the number of failures. So look, you can take n times p in order to calculate the number of successes. Well, notice that n is 57. And p is just 12 over 57. But guys, those cancel. So the number of successes is just 12. That's what we observed in our sample. So look, the number of failures, you can take n times 1 minus p if you want to, or the truth is you can just take our sample size of 57 minus 12. If you're not a success, it's a failure, so that would be 45. Those are both greater than or equal to 10. So our conditions are met, and we can proceed. So shockingly, what's the next thing we have to do is calculate the standard deviation, just like we did for confidence intervals. But look, we're not going to use the sample value. We're going to use the value from the null hypothesis because we're assuming it's true, and we're going to look for evidence against it. So p is 0.4. I want to multiply by 1 minus p and divide by our sample size of 57. So 0.4 times 0.6 divided by 0.57. If I take the square root of that, I get a standard deviation. I'll round it to about 6%. So then, look, now we can calculate a probability. So using this assumed value for the mean, assuming Westfield students are like everybody else, and using the standard deviation we just found, we can use our applet to find the probability of a sample value of a p hat. So when I say p hat, I mean this symbol of a p hat as or more extreme. So there's a phrase we've seen before. We just used it with simulations. I want to find the probability of a p hat as or more extreme. Or in this case, as low or lower than what we saw. What we observed was 21%. That's 12 out of 57. That's 21%. How likely is a 21% or even lower than that if the null hypothesis is true? Well, guys, look. If the null hypothesis is true, we got to put the truth in the middle. The 0.4 has to be in the middle. The standard deviation is 0.6, so one standard deviation above the mean would be at 0.46, and we're interested in how likely it is to get a 0.21 or lower. So 0.21 is over here, and lower than that would be this area right here. Well, guys, we can calculate that using our applet. So let me see if I can bring that applet reasonably well, if I can bring it into the screen. I can bring most of it into the screen here. So we'll begin our analysis of the normal distribution. Use, in this case, our mean is 0.4 because we assume the null hypothesis is true. And using that 0.4, we got our standard deviation of 0.6. So here is the normal distribution. I am trying to stretch it up. There we go. I can stretch it up. That's about as far as I can go. So there we go. So I want to find then, there's the 0.4 and the 0.46. So I want to find the percentage of my data, the area to the left of the 0.21. And I'll calculate the area. That area comes up to be 0.0008. 0008. So I'm going to label that. This is 0.0008. That probability has a special name. It's called a p-value. P for probability. And if the p-value is, if it is unlikely, then we do have evidence to reject that null hypothesis. If the p-value is not unlikely, then we don't have evidence to reject. So look, is that unlikely or is it not unlikely? Hey, that is unlikely. That's well less than 5%. So our p-value is 0.0008. That is well less than 5%. What we're saying there is that it is unlikely. So that means we can reject the null hypothesis. We can reject that 40%. So we do have evidence, not proof, but we have evidence that the real proportion of WHS students that, in this context, have had an accident while driving is less than 40%. So everything goes. All of the positives go together, all the negatives go together. It's less than 5%, so it is unlikely. So we can reject that 40%. So we do have evidence that Westfield High School's students are different. We do have evidence that the truth for Westfield High School is less than 40%. So let's do one more and go back and look at the iPhone data, which was the example that we did in class earlier in the week. So let's go back. 70 out of 95 randomly selected Westfield High School students had an iPhone. So our p hat, if you take 70 and you divide by 95, our p hat was about 74%. So Is that strong enough evidence to believe that the truth is more than 70% of WHS students have iPhones? Now look, the sample value is more than 70%, but is it far enough above 70%? Is it far enough away from 70% for us to be able to reject this 70% as the truth? And literally, I just picked this 70%. You could test whatever percentage you wanted to compare to. I'm choosing the 70% because I want you to see an example where we do not reject the null hypothesis. So to answer this question, the null hypothesis is we're just comparing Westfield High School students to 70%. So P iPhone equals 0.7. Let's assume the truth for Westfield High School students is 70% and see if we can find evidence that the truth for Westfield High School students is bigger than 70%. Just because the sample statistic, just because the sample proportion is more than 70% doesn't mean that the real truth underlying in the population really has to be greater than 70%. And that's what we're about to see. And all of this will look exactly the same. So checking the conditions, it's important that the sample is random. If it isn't random, you don't have anything useful. So same thing, our sample size here is 95. So 10 times 95, that's 950. That has to be less than or equal to the number of students in our population. We're well around 2,500 students. So approximately, independence is met. So here, for the number of successes and for the number of failures, what I want us to do on this example, I want us to be a little bit more specific. So for the number of successes, recognize that we want to take n times p, but look, p really isn't the number that we've observed in our sample. We've assumed that p is 70%. So really, the way that you check this condition when you're doing a significance test is you take the 95 times 0.7. So you get 66.5 successes. Of course, you can't have 66.5 successes. So what this tells us, though, is we've at least exceeded our boundary of 10. So the number of failures would be 95 times the failure probability of 0.3, and 95.3 is 28.5. Again, those are both greater than or equal to 10. So we are perfectly good to go. Our shape of our sampling distribution will be approximately normal. And now we can find our standard deviation. But just like we did before, I don't want to use the value from the sample. I want to use the value that we are assuming is true. And we're trying to find evidence against this value. So we're going to use the 0.7, 1 minus 0.7, and we'll divide by our sample size of 95. So that's the square root of 0.7 times 0.3 divided by 95. So if you round that, that's about 5%. If you round that to 2 decimal places. So notice, we're assuming the null hypothesis is true. So we're going to use that 70% for the mean. We're going to use the standard deviation above, and we can use the applet to find the probability of a p-hat. So notice, this time our sample proportion was higher. No problem. So we can use our applet to find the probability of a p-hat as or more extreme. So in this case, that means as high as 74% or even higher than 74%, because that's what we observed in our sample. So how likely is something that high or higher to happen if the null hypothesis is true? Well, guys, it's just like before. If the null hypothesis is true, what that means is that the 0.7 is in the middle. If the null hypothesis is true, what that means is that our standard deviation is 5%. So one standard deviation above the mean would be 0.75. So the boundary that I'm interested in is here, 0.74. So I'll label it up here since I didn't have room to label it down there. But I'm interested in being that high or higher. So this time, I want to find the area to the right of that. And what we are going to find, that probability, is called a p-value. It is the value of the probability. P for probability. So let's go back to the applet. Let's see if I can bring it back into the screen. So here, I want to calculate the area. I want to use this time my mean of 0.7. This time the standard deviation is 0.05. So there's the 70% in the middle and one standard deviation above the mean. But I want to change this to be to the right of a value, and the value we observed in our sample was 0.74. So notice this time we get quite a bit of area. We get a relatively large p-value. It's 0.2119 using our applet. But the only thing that really is different today is now we're interpreting that. We can use that probability, that p-value, in order to make a conclusion. So guys, this is not unlikely. So we do not have evidence against that null hypothesis. So remember, if the p-value is unlikely, we do have evidence against that hypothesis. This p-value is bigger than 5%. It's not unlikely, so we don't have evidence to reject that hypothesis. So I'll fill it in again just like we did before. Since the p-value of 0.2119 is not unlikely, and again, our boundary for that is 5%. So it's greater than 5%. That's what it means to not be unlikely. This is relatively likely. This is going to happen 1 in 5 times just by chance alone. So here, this is not unlikely. It's greater than 5%. So again, we cannot reject the null hypothesis. All of the yeses go together, all the affirmatives go together, and all the negatives go together. So this is not unlikely. So we cannot reject that null hypothesis. It might be true. So we don't have evidence that the true proportion of WHS students that own an iPhone is greater than 70%. So again, it's important for you to understand that I made up this null hypothesis value strictly because I wanted to show you an example of a situation where we didn't reject the null hypothesis. So as a researcher, you may choose what value you want to compare to. You just have to justify why you care about that particular value. So in the first example, that's why we were comparing to a null hypothesis value of 40%, because 40%, we have some evidence that suggests 40% is what's true for the population. Well, we were able to reject that 40% in favor of an alternative that maybe for Westfield High School students, in truth, they have accidents at a lower rate than first and second year drivers in general in the United States. So I just wanted to be able to show you an example of what it looks like to reject the null hypothesis because something is unlikely. And here's a case where we didn't reject the null hypothesis because something happened that was not unlikely.